All right, y'all. So today we are going to take a look at what we have been talking about with electron configuration and how that is going to lead into how bonds are formed. And so we're going to look at another visual representation using that electron configuration and orbital notation to help us figure out how atoms come together. Why is it H2O, not H5O or HO2? Why are these things happening? Okay, so as a reminder, your valence electrons are going to be those ones in the highest energy levels. So, if we had 1s, 2s, 2p, and we had these arrows, like that. Okay, so that would, this is nitrogen right here. If we were talking about nitrogen, then the highest energy level, remember these numbers in front are your energy levels, right? They're that principal quantum number. So your valence electrons here are 2s2 and 2p3. Okay, so again, looking at that highest energy level. All right, that is telling us what those valence electrons are. Now, also keep in mind, okay, if we were talking about, something that ended in, let's say, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Well, your valence electrons are these 4s2 because that 3 of the 3d3 is that lower energy level, okay? So it won't count in terms of your valence electrons. Again, looking for that highest energy level. So octet rule, it says that all atoms want to have a full valence layer, right? So when you're talking about those orbital notations, atoms want to fill it up, okay? So if you think about some of the ions that we did in our last unit, those numbers I gave you for their charges were very intentional. If you noticed when you did their electron configuration or orbital notation, that last energy level each time was full. It was always S2P6, S2P6 every time I gave you those charges. And how this happens is atoms are either going to gain, lose, or even share electrons with each other in order to get that full octet. And when that happens, when there's a losing or a gaining, it's an ion. But a sharing of electrons will not create an ion. And that's very important to distinguish between. So let's take a look. Let's see when these things come together, what is going to happen, okay? So here we go. So this is regular old oxygen. And as you can see here, right, we technically have this empty space right there and right there. There are those two empty slots in oxygen remaining that could have electrons. And so what happens is that oxygen then adds these two electrons. It will get it from something. Something has the ability to lose two electrons, or it can lose one, so it does it twice, whatever it might be. But right down there, we have this gaining of two electrons. And so that's what causes that -2 charge. Okay, so when we talk about things that are likely to gain or lose electrons, the periodic table is going to be our guide. So notice the one like up on the wall or the paper copies I have given you, they have this little zigzag down. All right, and that zigzag is separating our metals from our nonmetals. So the majority, right, like all of this, okay, are metals. So the majority of the periodic table are metals, and they are going to lose electrons. And then there it is. Our nonmetals, which is this top little corner, are going to gain electrons. But it's also important to note that these noble gases, remember we learned that word, the noble gases here on the end, they already have 8, right? It's S2, P6, S2, P6. They're already full. So these typically don't even participate in a bond. So that takes down our number to even a smaller amount that are going to be our nonmetals in terms of participating in bonding. But again, it's really important to distinguish that metals are going to lose electrons and nonmetals are going to gain electrons. Okay, and so this idea of losing or gaining electrons is going to lead us into what we call Lewis dot diagrams. So Lewis dot diagrams are going to be a visual representation of how these atoms bond with one another. We're literally going to show valence electrons, okay? So, and they're with dots. That's why it's called a dot diagram. Instead of arrows anymore, now we're using dots, lots of visuals when we talk about the atom. And this is really going to help us understand these bonds. So the way they work, all right, is in the very middle of our atom, you're going to put the symbol for whatever that element is. Okay, so let's say we were talking about boron, right? Okay, so the symbol for boron is B. Then again, we're only showing valence electrons. The electron configuration for boron is 1s2, 2s2, 2p1. Okay, and so our valence electrons are these 2s2, 2p1s. If you also think about the orbital notation for this, you have 2s and then 2p. For 2s, we would do up, down, and then for 2p, there would just be one by itself. When we do the dots for our Lewis dot diagram, they follow that idea of our three lines. So S, right, has one orientation. And then think about how P has the three orientations. That's the other three sides of your element. So here, here, here. It's an easy way for us to show our electrons as we do this. So boron, right, we think about the top representing S. It was 2s, 1, 2. And then it was 2p1. So we would just do 1 right here. Okay, let's think about a different example. Let's get rid of all of this. There we go. Okay, let's say instead we were doing, I don't know, nitrogen. Nitrogen is 1s2, 2s2, 2p3. Okay, so when we think about its valence electrons, we have 2s, 1, 2, 3, 2p, and the electrons that go in, 2s, 2, 2p, 1, 2, 3, right? 5 valence electrons for nitrogen. So we would have our element, nitrogen. Over here, we had 2s2, so s2. Then we said 2p3, and then Hund's rule works for Lewis dot diagrams the same way it does for orbital notations. So the way we did 1, 2, 3 on the separate lines, we are going to go around and do 1, 2, and 3. So that is the Lewis structure. I don't know why those keep erasing, for nitrogen. So here are just some more examples for your notes just to have. So you can see it's like 2s1, 2s2, 2s2, 2p1. And then we have this thing that happens with carbon. And this is why there's a whole course called Organic Chemistry studying carbon, is because carbon has this magic annoying ability where it, instead of doing what every other atom does, it splits that top one apart and allows it to form 4 bonds. Again, this is our hybrid, beautiful, special thing. Every other element is going to follow these rules for our course. In the real science world, other things break the rules. But the only one I need you to understand breaking the rules is carbon, okay? This 4 hybrid feature, okay? So carbon actually has the ability to form 4 bonds, even though it looks like it should not be able to do that. All right, so let's just take a break, and I want you to give these 4 a go. All right, so real quick, lithium ends in 2s1, sulfur ends in 3s2, 3p4. So 1, 2, and then 1, 2, 3, 4. Lithium lost its dot. All right, and then potassium ends in 4s1, so it just gets its one little dot. Selenium, stop erasing my dots, computer. All right, selenium ended in 4s2, 4p4. So 4s2 and then 4p4. 1, 2, 3. And then just like Hund's rule, we come back and pair it up. Okay, so those are your Lewis dots there. So bonding, wherever you have that unpaired electron is where a bond is going to form. And so again, bonds can be formed by the losing, gaining, or sharing of electrons in order to get the full octet. It's not just like a random number that are gonna share or lose or gain, whatever. It's in order to get that full octet. So the first type of bonding, we're gonna look at something called ionic bonding. So the key here, so ionic bonds are happening when things are losing and gaining. Okay, so when something loses electrons or something gains electrons, right, it forms a charge. Okay, right, we know that. And so cations and anions are the words that we are going to use when these things happen. So a cation right here, okay, your cations are formed when an atom loses electrons, creating a positive charge. Okay, cation is formed when an atom loses electrons and therefore has a positive charge. Anions are formed when an atom gains electrons and therefore has a negative charge. Okay, so cations are positively charged, anions are negatively charged. And so when these things are coming together, they come together in this like perfect ratio where they end up being something neutral. The amount lost always is going to equal the amount gained when we are forming a bond. So let's take a look, for example, sodium and chlorine. Okay, so sodium ends in 3s1. Those are the valence electrons for sodium. So Na, and it's got that one beautiful valence electron. Why does it keep doing that? Then we have chlorine. Okay, chlorine ends in 2s2, 2p5. So 2s2, 2p1, 2, 3, 4, 5. Okay, and so that shows us that we have this empty space left right there on that chlorine, right? So if we're picturing even the orbital notation, there would be that like one empty spot left in our p orientation. And so what happens is this sodium, that like one electron sodium has, can go right there. And so you've probably heard of NaCl. That's something a lot of us have heard of before this class. And so literally you have Na, it has given its one electron, and then you have chlorine, which had 1, 2, 3, 4, 5, 6, 7. And so if you took your hand and you actually kind of covered up this sodium, like if you just kind of put your hand over the screen, you will look and you will see the chlorine now has 8 dots around it. And that is the whole point, that full octet. When sodium gave that one electron to chlorine, chlorine gained that one electron, and now it has 8. That is why sodium chloride, again, this thing we've heard of, is NaCl. Okay. But we didn't just talk about losing and gaining. That third part of the definition of how bonds are formed was about sharing electrons. So losing and gaining, great. We had that metal giving it to the non-metal. Beautiful. Covalent is going to occur when atoms share electrons. Nothing's being lost, nothing's being gained, so there are no charges involved here, right? If you're not losing an electron, then your charge doesn't change. If you're not gaining an electron, then your charge doesn't change. You're simply like sharing them to make that happy octet happen. The key part here is that this is typically going to occur between two nonmetals. So just as a recap, we're talking about this little upper quadrant, upper little triangle of the periodic table, typically when we're talking about those covalent bonds. So let's take a look at an example here. Okay, this one's a little bit trickier. All right, so nitrogen and fluorine. So nitrogen ends in 2s2, 2p3. Okay, so 2s2, 2p, 1, 2, and 3. Oh. All right, then I'm telling you I have fluorine. Fluorine. 1, 2. I'm sorry, it ends in 2s2, 2p5. 1, 2, 3, 4, 5. So when we look at these, they both have this space where bonds can form. Fluorine has space right here. And then nitrogen, though, it needs 3 electrons. So it's kind of easy to see how initially, if you took that nitrogen, which had those 3 empty spots, if you smooshed those together, 1 fluorine could pop in right here, right? And now that fluorine is happy, but the nitrogen is still not. And so these are actually kind of like little puzzles you have to like figure out how to make them work. So nitrogen still has these 2 empty spots. I am telling you that the only atoms involved here, though, are nitrogens and fluorines. So what happens is you bring in another fluorine, right? Fluorine has that 1 empty space. So we can put that empty space from another fluorine and then keeping in mind the rest of it was full. Great. Now there's a whole nother empty space on that nitrogen. And so a fluorine has to come in again. So it comes in right here. And there's its unpaired, okay? And then keeping in mind the rest of it was full. And so this is what actually happens for nitrogen and fluorine when they come together. It is 1 nitrogen and 3 fluorines necessary to make that formula. So when you are looking at 2 nonmetals, you got to get a little like puzzly, a little creative in figuring these out. So what you have here at the end is you have 3 different ones for you to try in your notes. So I'd like for you to take some time and really struggle with them, give yourself grace, and then do all 3 before you come back to the video, okay? Again, the idea is that something is losing, sharing, gaining, right? We have these different things that can happen for electrons in order to get those 8 dots around an atom. And so what was different with covalent is that we were seeing 8 dots for everybody, whereas when we were looking at the ionic example, we only have these 8 dots around chlorine, because sodium literally gave away that electron, whereas here, everybody was just sharing. They were sharing their electrons in order to get that full octet. So take a beat. The video is going to stop, and I want you to work through all 3 of those next examples, okay? Work through all 3, then come back to the video. All right, so calcium ends in 4s2, so there's its 2, and oxygen ends in 2s2, 2p4. And so what you can see here is that that oxygen has these 2 empty spots. And what's great about this example here is that calcium has 2 to give, oxygen needs 2. And so calcium literally just is like, whoop, you can have 1 and you can have 1. Done. It can just give those 2 electrons for the 2 that oxygen needs. And so it's like not beautiful, like perfect picture where they like just smoosh together because you have those 2 being shared. So when you draw this, you could either draw it like Ca And then we had our O, which looked like that. You do not need to use separate colors for these. I just do it because I think it's clearer for students to learn by seeing the colors. So you could draw it like that, where you had the calcium on the side, or because the other empty spot was on the bottom, you could draw it on the bottom. It truly does not matter to me where you put it, because the idea that I'm looking for, sorry, don't put that on the side. I was just, the idea is that you are seeing that calcium. You only need one calcium because it gave these 2 electrons. Okay, so again, don't draw the word calcium twice because the individual calcium gave 2 electrons. All right, sulfur and chlorine. So sulfur ends in 3s2, 3p4. 1, 2, 3, and 4. Whereas chlorine, really wish you would stop erasing my dots. Chlorine ends in 3s2, 3p5. 3s2, 3p1, 2, 3, 4, 5. So 1 opening for chlorine, 2 openings for sulfur. So we can start, and we know that our chlorine at least has that 1 empty spot where one of our sulfurs can come in, right? But we still have that other unpaired spot still empty on our sulfur. So the chlorine got happy by smushing 1 to 1, but the sulfur is still not done, right? This is where the idea of something else has to come in to make that sulfur happy. And I am telling you again that only sulfur and chlorine are involved. So takes another chlorine in its unpaired spot, and then the rest of it was full to come in. So when sulfur and chlorine come together, it is going to take 2 chlorines and 1 sulfur to make that bond happen. Okay, and then our last example, here we had potassium and selenium. So potassium ended in 4s1, so okay, with a 1. And then selenium is 4s2, 3d10, but again, that 3d is less than 4, so they're not valence. So 4s2 and 4p4. So selenium, oops, let's use a different color. And then P4. So here is our selenium. And we can see now that we have this unpaired space here and here, where the potassium has 1 to give. So that's pretty straightforward to see. Se, 1, 2, 3, 4, 5, 6. 1 potassium can come in right there. But when you look at this, the selenium, again, is still not at 8, right? We don't have a full octet. And again, I am telling you that potassium and selenium are the only elements involved in this. And so the selenium needs something else. We're not going to bring in another selenium because that brings in way more unpaired stuff. So we bring in another potassium, which had the 1 unpaired, and it jumps in right there. And so it takes 2 potassiums and 1 selenium to make this happen. And that is how bonding works. that is it, friends. These unshared, unpaired electrons, they come in together and they make this full octet. And that is why potassium selenide will never involve like 5 potassiums. Nope, there's only 2 empty spots on that selenium. So the potassium slide right in. It's why water is H2O, all of these things. So those orbital notations led us to electron configurations, which helped us figure out how many unpaired electrons we had. And that led into how these bonds are forming. So again, as a wrap up, ionic bonds are forming when something lost and something gained. So like here, potassium lost, selenium gained. And covalent bonds are when something shares electrons, like here. Sulfur didn't lose these electrons. Chlorine didn't lose these electrons. They shared them in a way to get that full octet. So there you go. That is your bonding.